This is the lecture 10, first segment, but this is the last lecture in this course, and we will begin with some revision. Means we will review the few formulas for the applications of the theory of residues for computations of definite integrals, Riemann definite integrals. So let's begin. So we were talking about several types of integrals. So we have here type number 1. And it was integral of the type, so let me put it like this, I was equal integral from 0 to 2 pi, so this was a trigonometric integral. So here R was standing for the rational functions, so this was cosine z, and here we have a sine of z, and this was, I'm so sorry, t. What's happened? Okay, t, and this was sine of t dt, and then we have this integral can be written as the integral over the unit circle c. So put here c is the unit circle. And here we have here r, and here we have here z plus 1 over z divided by 2, and this is z minus 1 over z divided by 2i, and then this is dz divided by I z. So let me put my glove because my hand becomes sweaty and that is distracting me. Now, of course, you should understand that if we put here that your function f of z is exactly the function r, and this is z plus 1 over z, 2, and this would be z minus 1 over z by 2i, and this is 1 divided by iz, then this integral can be computed using the residues. The residue theorem, namely you take the of all, let's say, take of all singular points inside the circle, and then you will write it down. This is residue of this function, f of z. So this will be f of z at the point zk. So that's the type 1. And the type 2. So let me point out, so here we are having the, so this will be inside the circle, so let me make a small picture, so just to keep you aware that singularity, there may be all kinds of singularities outside and inside the circle, outside and inside the circle. And this one's like 1, 2, 3, those are your zk. So only those inside are counted. So the type number 2, is different. It's the improper integral, so this is type number 2, and this is improper integral of that type, so put it like this, I is equal integral from minus infinity to infinity. And now I put here like just simply f, and this will be of x dx. So here we have here that f of x is again a rational function rx, and this is polynomial px divided by qx. So we have here the degree of p, and this one is plus 1 is smaller than the degree of q, so that's my first assumption. B, that q of x is never 0, and yes, that's it. So all the singularities have to be either in the upper plane or lower. So let me make a picture. So we have here the real axis, imaginary axis, and we are looking at this portion here, at the above. So let me remove the lower part. So this is removed. We ignore that part, and we only look for the singularities in the upper plane. So those are the zk, and then we can write the formula. So then this integral will be equal to pi I, and this will be sum of residue, and imaginary part of zk must be positive, and this is residue of f of z, and here we have zk. So that's the second type of the integral. We discussed it last time, and we also consider this type number 3. Namely, we are looking for the integral from minus infinity, so this is my I again, to infinity, and now we have e to the power I, a, and I put here x, this will be f of x dx, and let me check if I, yes, dx, so here of course f of x is again the rational function, so this is p of x divided by q of x, as we have here the assumption, so the degree of q is larger than the degree of p. B is as before, the q of x is not equal to 0, and c is that a is positive. So those are our assumptions. And then this integral again can be related to the picture above. So this is again the same picture. It relates to these two cases, and we can write the formula that was derived, and this formula simply says that this will be equal to pi I, and then we are getting sum of the residues. So again the imaginary part of zk must be positive, and this is residue, and this is the function ei a z f of z at the point zk. And then it was also noticed at the end of the lecture 9 that this particular integral actually computes you two integrals, namely if you rewrite the number, let's say this complex number, let me write it here, e to the I a x, this will be just simply equal to cosine ax plus I sine ax, then maybe I sine ax, put it in the brackets for safety. Then of course the integral I can be split in two integrals, and we are having immediately from this formula we are getting the formula that call this is 3a, that this integral under the same assumption, so this will be infinity not e, put here cosine ax times f of x dx will be equal, this will be real part, and then we put here 2 pi I, and then we have here sigma, and this is imaginary part of zk larger than 0. This is residue, again the same as above, az times f of z zk residue. too crowded? Yes, too crowded. I will rewrite this formula. I'm sorry. This is a little bit. We need more space, so I will just rewrite this formula in a more spacious way. I started exactly here. So put it like this: integral minus infinity, and this will be cosine ax, and there's the function f of x. That's the rational function, and then we have here real part and big bracket 2 pi I sigma, and this is imaginary part of this singularity must be larger than 0, and then you have here residue. This is e I a z f of z z k, close it, z k k, close it, and close the second bracket. So this will give you the 3a, and 3b will be immediately this formula. So this will be integral from minus infinity to infinity, and this will be sine of ax f of x dx is equal to, this will be imaginary part of the same formula here. Imaginary of zk larger than 0, residue e I a z f of z z k, close and close, and we have this too. So that's the present situation. This is what do we have. We have here these three formulas, for let's say more than three, okay, actually it's 5. We have here the 5 formulas. So first of all, you have here the integral of this type, and you have to understand that that one is the formula that allows you to compute the type 1. So the formula number 2 is actually allowing you to compute the integrals of the rational functions. That's the number. So this is, sorry, I skip it. This is this formula, and the last formula that I have with the exponential factor allows you to compute, and we put it here, this trigonometric, mixed trigonometric and rational function integrals. So what do I see? I see this one and that one. And let's play and let's apply this formula, and let's try to compute some examples. So maybe begin with something. Example number 1 related to the trigonometric formula. So let's start. And okay, so compute the following improper integral. And now integral is just simply I is equal, and let me copy the integral. So this is minus infinity, this is x, and this is cosine x dx divided by x squared minus 2x plus 10. And immediately we recognize that this is corresponding to the situation when we have here e I x must be equal to the cosine x plus I sine x. So actually we can compute immediately, you can compute not only that integral but also the integral with sine. So namely we have here, maybe I will do it like that one. So why not we just simply add here another one. I will just simply add the additional integral like that and put here I, and this will be x sine of x and this will be again dx, and this will be x squared minus 2x plus 10, and you can see that this integral is actually the integral of the type number 3, where you have here EIX, yes, and then you have here x divided by x squared minus 2x plus 10, and put here dx, and by using the formula for type 3, we are getting this is 2 pi I, and there is only one singularity. Notice that z, maybe not here, maybe I put it here, that here that z squared minus 2z plus 10 equals to 0, if and only if z is equal to, and you have here 1 plus minus 3i, and clearly the only one of them, so which one is, put it like this, the imaginary must be positive, so this is your critical, let's say, singular point, which is actually playing in this integral. So this one is imaginary, or z0 larger than 0. So I can write it down. This will be residue of the function ei z divided by z squared. Just write it down under. Don't try to squeeze residue. And here we have here ei z, and this one is z squared minus 2z plus 10, and this is at the point 1 plus 3i. And you, of course, notice that this is a pole of order 1. 1 means simple pole. So the residue formula for that one is very simple, very easy. So we can rewrite it now. This will be 1 over 2 pi I. And then let's do it. So put it like that. I take the value here and I put here ei, and this replaced by 1 plus 3i. And this one is 1 plus 3i here, and here I'm getting 2, and this will be 1 plus 3i minus 2 times nothing. And this, of course, if you don't remember how it was computed, I refer you to the formulas for the computations of the residues at the simple poles. So you just evaluate the numerator at the value of the singularity, and in the bottom, in the denominator, you just simply take the derivative evaluated at that point. So now we can simply try our simplification, and we are getting the first, what we are getting here is the following. So this is equal e to the power minus 3, and then you have here cosine 1 plus I sine 1 times 1 plus 3i, and here, as you see, this will be just simply equal 3i. Something sorry, that's how you make mistakes. 6i, and that's how you make mistakes when you are don't paying attention. So you can make the first simplification, and then you rewrite it down, and you are getting here that this is equal 2 pi. I put here 6, I put here e minus 3, and evaluate this product. So I'm getting this is equal cosine 1, and then this is minus 3 sine 1, and this is plus I, and this will be sine 1, and this will be plus 3 cosine 1. Close it, and we can write the answer. The answer is that answer, put it like this, answer. The integral, the first integral from minus infinity to infinity, and this was x cosine x divided by x squared minus 2x plus 10 dx is equal to the real part, so this is nothing else than this is pi over 3 e to the power 3 multiplied by cosine 1 minus 3 sine of 1. And the second integral is the imaginary part of this above expression, so you are getting here x, and this will be sine of x dx, and here x squared minus 2x plus 10 is equal again the same factor e to the power 3, and this will be sine 1 plus 3 cosine 1. So this basically is how it works, and we could do several other examples, but before we go to these examples, let me, let's say, make some things more precise. For a moment we're talking about let's say about the integrals, which are improper integrals, so maybe recall all the related definition, recall. So to be more precise, a function and an integral of this type, and I put here like this, minus infinity infinity f of x, any f of x dx is actually equal to the two limits. So first of all, you have to write it down as the two integrals. So this is first improper integral, and then you write it down from 0 to infinity, second improper integral. And in such a case, if this limit this will be minus n 0 f of x dx, and if this limit exists, so if they exist, assume they exist, this must exist, and this must exist, then our improper integral is exactly called that these values, these two values. So remember, the integral from minus infinity to infinity, precisely speaking, denotes two improper integrals. One is at minus infinity, another one is at plus infinity. Both of them are limits. Both of them are limits. So in such a case, we say that the improper integral converges, and the associated, let's say, and the corresponding values of these limits give you the value of this improper integral. But there is also another option of looking at the improper integral. So maybe this is also interesting, so we should specify it. So in such a case, if you have here, for example, if you take this improper integral and f of x and dx, and here I'm not writing here equality because it is not equivalent to the previous one. Instead of splitting it into two integrals and two different limits, I will just take one limit. I put here limit as n goes to infinity, and then I put here that this will be minus n, so both of them go to minus infinity, f of x dx, and assume that this integral, that this limit exists. So in such a case, it may happen that the integral itself is divergent, but this limit exists. So examples can be easily written, but in order to be more precise, we just simply say that this is not the improper integral in the usual sense, and we will put it like this, PV. and we'll call it principal value of the improper integral. We'll call it principal value of that integral. So please remember, if the integral actually is convergent, improper integral, convergent integral, so of course it also has a principal value. Principal value in this case will be exactly the same as the value of this integral. But it may happen that the principal value is different, and there are examples of integrals which have principal values. We'll see some of them maybe here. Some principal values which is finite, but integral is divergent. So I should also mention that although this principal value seems kind of, coming out of nowhere, but it is a useful concept and it is used very, very successfully in many areas of applied sciences, especially like physics, quantum mechanics, and they actually apply the concept of principal value there almost as freely as improper integration. So that's what it is. So maybe now, if you look at this particular situation, you can say, why not to extend this? Why not to extend this to the different type of the improperness? So, for example, suppose the following. Suppose like this. Here, so I put it like this. Suppose here we have the function f, and put it like this, from an interval a and b to r, and I am not really good because I wrote it a and b, and I want to exclude one point. So that means my function has a singularity at the point c. So you have here a and c is in between, and is b. So examples of such a function, for example, if you write it down, this will be like f of x is equal 1, and this is x minus c. So definitely cannot divide by 0, so c is a singular point. So in such a case, that's the example. Maybe I should not write it like this. Singular point. And then you would like to see maybe a similar concept of the let's say improper integration could be applied to this type of singularities. Namely, if you would like to consider it to be like a regular singularity, and you would like to say, okay, this integral, if you would like to write the integral from a to b of f of x, so dx, of course, you have to understand this would be integral from a to c, so this is first portion, and since here c is a singular point, so put it in red, so that's improper integral. There is no value at the end point. And then, of course, you have here another, and again, this will be from improper place, means from the singularity to b, and again, f of x dx. So in this case, what we are getting here, we are getting again two limits. So here we have here limit, and I put here like this, maybe not epsilon, okay, maybe epsilon going to 0 from the positive side. So I put it like this. This is a minus, this is correct, 8, and this will be c minus epsilon f of x dx, and then you go here and limit again, delta goes to 0 from the positive side. So then this will be like a c plus delta to b f of x dx. So again, in such a case, this is an improper integral. And this improper integral is convergent if that limit exists, and that limit exists, finite limits, and then you can associate to this integral the values of these two limits as the value of this improper integral. But there is also a version of principal value that you can associate here. Why not to do exactly the same? Principal value, and here I put here this integral a b f of x dx. That means the principal value will be just one limit. This will be just one limit. Namely, I put here like this, 1 epsilon goes to 0, and then you put here a to c minus epsilon f of x dx plus, and here will be c plus epsilon to b f of x dx. So still split it, but that's the one limit. And then many cases, like in the case of that example, so for example, take that one, principal value as an example, compute this from minus 1 to 1 of dx x. We know that this integral, improper integral, is divergent, so this is divergent. But I'm computing here principal value. So let me do it accordingly to my definition, and here I will be getting this is limit, epsilon goes to 0, and here I'm getting here integral from minus 1 to minus epsilon, and this is 1 over x, and then you have here dx, and then you have plus, and this will be integral from epsilon. Stopped working, 1, and this will be again 1x dx, and before we compute the limit, we evaluate this integral. So what we are getting here, this is limit epsilon goes to 0. Oh, we know how to do this. This is ln. And of absolute value of x, and I put here like this, from minus 1 to minus epsilon, and plus ln, and then you have here x, and this will be from epsilon to 1. So let me write it down. This is the same limit, so this will be limit epsilon going to 0, so I'm getting here ln epsilon minus ln of 1. Ln epsilon minus ln of 1. And this one is equal to, and this one is equal to ln of 1, and that one is, sorry, plus minus ln of epsilon, and then we get the cancellation. Oh, epsilon is so I'm getting just 0. So principal values turns out to be 0. So that means in such a case, even if this integral is divergent, we can say that in this case we can associate it with this integral a number called the principal value of this improper integral. In this case, this value turns out to be 0. So let me continue this topic, and I will be interested now in the following situation, namely, what if actually I have a function, that has a let's say like this, let me let's say discuss a possibility of a singular point which is on the path of the integration, which is a path of integration. So for example, we are dealing here with the function f of x, so any analytic function, and suppose, so here this is real function, so here we have here singularity, so all the time my function actually has the singularity here, so call this my z0 is a singularity, and this is simple whole. And now let's say I'm trying to compute an integral So I would say like this, write it down, the integral from minus infinity to infinity of this function f of x dx. So I understand there is a singularity here. There is a singularity here. So I cannot compute this integral in the usual sense. So that means I will be trying to compute the principal value of this integral. So let me give you an example that this example we're definitely going to do. Let me check if I can still find it. Oh, probably somewhere. Where's my examples? Yes, found it. No, didn't find it. Oh. Yes. So example looks like that. Example. It's compute. Compute. And this is integral, and this one is equal to, and minus infinity, infinity, and here I have here x, and this one is sine, not x, just, I will be doing this integral, so I want to copy it correctly. So x squared plus 4, and I add here x plus 1. So now you can see immediately that here we have three singular points. Let me show you. This is the real axis. So we have three singular points. First one is 2i. Then you have here minus 2i. But there's also this point, minus 1. So this is the point which is singular, and this is on the axis, real axis. So what do I have here? If I look at this example, I have that the assumption that you have here like this. Remember, sorry. Yeah. I want to have here sine of x, just for the purpose of non-triviality. So we have here that our function f of x, in this case, which is equal 1, is equal x squared plus, not good, not space, I ran out of space. So f of x, which is equal 1 over x squared plus 4, x plus 1, so which is px and q of x, has violated the assumption. This is not different than 0. Denominator is not different than 0 for x real. So that is violated. That assumption is violated. So let's look and recall how the whole process was done. So let's go revisit this particular integral, and namely we have again the situation, and I put it here like this. This is like a minus infinity, infinity. We all started with this integral, ax, and then we have here numerator, and then we have here denominator, and then we have here this integral that we were studying before. So our f of z is equal p of z divided by q of z. And now let's assume that this is not exactly like it was before, because here we will say simply that p of z, so that means that we have here degree of p is strictly smaller than degree of q. This is the same, the second one, that a is larger than 0, and instead of c, maybe we put it like this, that q of x is different than 0, except for some singular points. So let's say simple poles, simple, maybe put it in red because it's important. Simple poles, simple poles at add, it will be like a add, and call it like this, C1 CK, C1 CK. Very good. So I have simple poles now. So how did we do it? This integration. We started with the contour. So let me make a picture first. First of all, remind, we ignore that part. Now we have singular points. I may have here, here, and also I don't exclude, I may have here singular point, simple poles on the axis, real axis, simple poles. So of course that one appears with the pairs, so with the other one. So those are my singular points. So what did I do? I took a contour, a big contour, semicircle, and this semicircle contains all the singular points in upper half plane inside. But we have a new singularities, and these new singularities are at the point C1 and put here like this CK. So how can I deal with this? I'm going that direction and suddenly on my way there is a singular singular point, which means something, the function like explodes. It's not a good thing. So I will go around it. I will just go around it. And then I go here and I take it another detour and goes. So in such a case, I will have that one will be big circle. So this is R, this is my value R, and those are my small circles, semicircles. So this will be negatively oriented, notice. This is negatively oriented. So this is like a K1 epsilon, and this will be minus KK epsilon. There may be more of those points. More of those points. So I look at that one and I say, okay, so what really happens? Really happens is that I have here a kind of situation. Suppose here the g of z is a function, it's an analytic function. General analytic function, this g of z, in our case it will be EIAZF of z. And we have a singularity, simple pole at z0. So where is it? So I'll put it like this. I have here simple pole at z0. And then what happens here? I take this integral, this one goes that way. You see, this goes that way. So that's why I'm going to reverse it, and I consider a small epsilon, so this will be my epsilon, K epsilon, semicircle by that direction. Let's compute it. It's not a whole thing. It's not a whole, but this is half of it. Let's compute this particular integral. Let's compute this particular integral. But that's not difficult. So now let me do it. So I say like this, integral over K epsilon, and I put here g of z dz, and let me write it down. What do I get here? Okay, I can use the Laurent series expansion. So that means my g of z, this is a simple pole, so it starts like a minus 1 z minus z0 plus a0 plus a1, okay, plus a1 z, not nice, plus a1 z minus z0 and others. So I can rewrite it down. So this is a minus 1 z minus z0, and that one is plus a0 plus a1 z minus z0 and plus 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 and dz. And I know how to compute it. I know how to compute it. That one is easy because I can choose the parameterization. Z of t is equal to epsilon EIT. T belongs to 0 pi. So I can just rewrite it down. This epsilon goes out. This one is 0 to pi. Maybe. Just start term by term. So this will be a minus 1 and 10 a minus 1. And here we have here integral, so that will be antiderivative. Okay, I just simply write integral from 0 to pi, and that one will be dz, so this will be epsilon I, and this is EIT dt, and here I'm getting here, I forgot, this one is not exact, here. Z of t is equal, I'm so sorry, epsilon EIT, so that one will be EIT, and in the bottom minus, so this will be epsilon EIT dt. So that's the first one. The second one is just a differences, so you're getting here that this will be equal to A0, and this will be Z0 plus epsilon minus, sorry, actually it's minus epsilon minus Z0, and this will be minus epsilon, and then plus A1, and this will be the same except this is Z0, and minus epsilon square minus Z0 minus plus epsilon square, etc. So now I concentrate on the first one. So what cancels? This cancels, this cancels, this cancels, this cancels, and I'm getting here, this is a minus 1 times pi. And here I'm getting here, this one is equal, and I can put it like sum n is equal 0 to infinity, and then we have here an, and this is z0 plus epsilon to the power n plus 1 minus z0 plus minus epsilon. Sorry, checking. You started, yes, or opposite. So this is a minus, this one is plus epsilon to n plus 1 divided by n plus 1, and then take epsilon going to 0. So what I'm getting that this is just simply equal to pi I, 2 pi I, and that one is 0 because these two values will eliminate each other, so plus 0, because z0 to the power n the power minus z0 to n the power is 0. So we got it, so we can say, we can formulate what we got it. So in such a case, this integral limit as epsilon goes to 0 of this integral k epsilon g of z dz is equal pi I, and that one is equal to, residue of g of z at z0. Very good. Good. Okay, make a picture. And now let's go back to our integral and let's analyze the situation like we did in the case of the proof last time. So we know here that this integral just a second, I think I'm too far from the picture, so it will be very inconvenient. So contour R and epsilon. We have here small epsilons here, so this is the contour. So now you have the red contour is that one, it's CR. And then let me write it down. What do we have here? So let me write it down. So what I'm getting here, we are getting here the following situation. So 2 pi I, and this is the sum of the residues image of zk is zk is larger than 0, and then you have here residue EIA ZF of ZK, and then this one was equal, and then we have here like that. Integral over the big circle, so put it like this, KR, this is EIAZ, and then we have here F of ZK, no, F of, no, it's very ugly, difficult to write with this pen, AIZ, F of Z, DZ, so that's the first part. So which one? This is that circle, this circle. Now we go to that one. So maybe I call this all segments, I put it like this, epsilon R segment. So I call all these segments together as epsilon I R segment. So the second one will be plus, and this will be integral, and this will be over this, all segments. So this is small r and epsilon, the same function. But now everything is now real, so I can just simply forget z and write simply z. So this one is x, and this will be the x. And then I have also demicircles, but these demicircles are negative, so there is minus. So I put here sigma, and this will be like a L is equal to 1. So I know I made a, so put here n, put here n. So we have here k singularities. So then I have here this k, this is L, this one is epsilon, and then you have here E, I, A, Z, and this is F of Z, dz. And now we go to the limit. We go to the limit. So epsilon goes to 0, R goes to infinity, and what do I get here? I'm getting here that this limit becomes integral from minus infinity, infinity. This is E, I, A, X, F of X dx, but that one is now principal value, and the other one is minus, and here we get the sum of the residues. L is equal to 1, okay? And this is pi I, not 2 pi, pi I, and this is residue of E, I, A, Z, F of Z, and here we have the C, L. I will make it much nicer, so just give me a chance. So it's okay, and this is pi I, residue E, I, A, Z, F of Z, and this is C, L. So now you look here, and we see that that value is always constant. Doesn't matter what is n or what is r. So that means we are getting the formula. So new formula, including singularities. So maybe simple poles, and this will be like a C1, C2, CK on the real axis. And then we are getting here that this integral from minus infinity to infinity, E, I, A, X, F of X dx is equal to pi I and sigma, and this one is equal image, of zk, not zk, zn positive, and this is a residue of f e I a z f of z z n plus, and this will be pi I, and we are getting here the image, not image, so this is ck, so real numbers. This is C. So just simply write L is equal 1 to K. So those are CK are real, CK, remember, real poles. So those are here. So what am I getting here? Residue, again, E, I, A, Z, F, Z, and this will be C, I. And that's the formula. So we derive, we know what to do. So that to do. So once you have this formula, you have the answers. So just remember, why do you need to know this formula? And you have to practice, because once you have an integral, like I mentioned, so let's do the integral example. And my integral looks like this. Integral, compute, and I put here like this, integral, and this is minus infinity, infinity, and this was sine of x. This is x squared plus 4, and this one is x minus 1 dx. So you can immediately recognize that z squared plus 4 z minus 1 equals to 0, so you're getting z1 2i, z2 is equal minus 2i, and call that one just c is equal to 1. So those are the poles, and that one is poles. All of them are simple poles, but that one is in the lower half plane. So that means it is excluded. So this one is in the real numbers. This belongs to the real numbers. So I can write the answer. So maybe I write the answer for this integral. So because basically I prefer you to practice with the ix rather than sine and cosine, because you will notice it on the exam that many people make mistakes. Just simply one moment. Just simply because they mix up exponential with the sine or cosine. So we can write the answer. So this will be 2 pi I, and now you can say this is the singularity that I'm taking here in account. So this will be residue of this will be e I z. Yeah, I tell you, if you write sine, many people say, oh, sine, exponential, sine. No, always. Remember, always associate this integral to this function, exponential function. You will not mix them up. So 10 you have here divided by x squared plus 4, and this is x minus 1, and this is at the point 2i, and the remaining parts is pi I, and this one is residue, again the same function, except you see now this is on the real, so there is no 2. Here is a 2, but there is no 2. And then this one is equal to, this is z squared, z squared plus 4, z minus 1 at the point, looks like n, and this looks like at the point 1. So let's compute it. So the first residue is almost, you can do it in your memory. So what do I get here? So remember, so you have here, you can take that one and put here I, so this is 2i minus 1, so this is equal e, and this will be minus 4, and then divided by divided by, and that will be z minus, so this will be 2I minus 1, and here you take the 2t, so this is 2, so that means 4I. We know how to compute the residue. Then you go further, this is pi I, and then you are getting different ones. So now you are getting here that this is residue. So in that case, what I'm getting here, this is E, this is I, divided by 5. 5. And then 2 pi I, and here I have simplification. I can cancel this I, so that's the first simplification. I can cancel this 2. So let me just simply simplify it. So this will be like a 1/2. This will be e to the minus 4 divided by 5, and this will be minus 1 minus 2I, and this will be pi, and here I have here pi I, and then you have here also divided by 5, and then you have here cosine 1 plus I sine 1. Do I do 1/2? And then simplify it, so I'm getting here real part is okay, e to the power minus 4 divided by 10, and this will be minus, put here minus, and from here I'm getting here again another minus, and this will be, where's my pi? Pi, yes, there is a pi. Pi, I lost pi, I found it. So this will be pi. Okay, maybe clean it. So this is pi, so real part, so this will be minus, and this will be pi e to the minus 4 divided by 10, and that one is minus, because this is real part, so this is minus, so this is minus, and this will be pi over 5 sine 1, and this will be plus, and this will be again I, and that one will be pi cosine 1 divided by 5, and that one will be minus pi e to the minus 4 divided by 5. I simplified 2 by 5. So I can write the answer. So you write the answer. The integral in question that we are computing, minus infinity sine of x divided by x squared plus 4x minus 1 dx is equal to the imaginary part. So this imaginary part, it's sine, so it's imaginary part. So put here like this principal value. So we understand that that is understood in this sense, that this is 5, and this is cosine of 1 minus e to the minus 4. And that's the answer. Actually, we computed also the other one. Actually, we also computed that one. So why not to write the answer as well? So this will be cosine x dx, and this will be x squared plus 4. This is x minus 1, and that will be pi over 10, maybe minus, put here minus. I think I made a mistake. This one, this is plus. Yeah. So this is minus pi over 10, and then we have here e to the power minus 4, and this will be plus 2 times sine of 1. And that's the example. That's the example, and I believe that it is kind of the reasonable to believe that this type of the examples are to be considered as a nice examination questions, especially knowing that exam is like a open book exam. You can go anywhere you want to check all your notes, check your classes, check everything what you have basically accumulated during this semester and compare your way of doing it with the way that was given to you as practice or as examples. And then, of course, I'm having a high expectations. You will probably do very well with this type of the problems on the exams. I'm so sorry, but usually, it is not kind of my habit to reveal the examination questions, but I should say yes, there will be a singularity on the path of integration at the at one of the examination problems. And this time there will be 5 problems on the exam, so one of them can be definitely with the formula corresponding to formula this, or maybe another one, because as you notice, this method can be extended. So good. Maybe one more remark. If you put a equals 0, did you notice that you are actually getting the integral of type 2? So I can always change it to that position. So that means actually you can say not exclude 0, because this would cover the previous type of the integral. So that's why I'm not excluding it, and you will have an opportunity to practice before the exam. I will give you some examination problems that will help you with the preparation. Thank you.